Okay, so hi guys. I'm going to speak a little bit about reinforcement learning, but just the tip of the iceberg, kind of surface level stuff. So reinforcement learning is a type of machine learning where an agent learns how to make good decisions by exploring its environment through trial and error. It is essentially trying to make decisions that will get it the highest reward within its environment. So the idea is that an agent would, well, start at some state in the environment and it will take an action exploratively, it'll take an action, and then as it transitions to a new state, it would be given a reward by the environment. Let me actually get out of this. Let me just edit this. So like I said, it will start at a state, it will take an action, and then it will be given a reward as it transitions to the next state. And then it will take like another action, get a reward from the environment as it transitions to the next state. Let me just say double prime. So that is kind of how it goes. Okay, let me get back to my presentation. So reinforcement learning agent doesn't just care about getting one reward. It's not just like that. It tries to actually sum up the rewards over time so that it's essentially is always making good decisions. When it starts at a state and goes through the process, it is actually, you typically want it to reach some form of goal state. We call them terminal states. Going from like a start state to a terminal state, we call that an episode. And a terminal state could be the goal, like me finishing this tech talk, or it could be some disaster, like a robot falling into a hole. But essentially, it wants to accumulate, get the highest rewards it possibly can in total over the training course, over many episodes. So this is one of the algorithms that I particularly want to talk about. Q-learning, it's a value-based algorithm. There are other types of algorithms. There's a value-based and policy-based. So a policy, which is represented by this pie, this algorithm tries to estimate the optimal policy. And a policy is a function that takes in a state and gives you an action. It's essentially the brain of an agent. So in this algorithm, I'm just going to mention the parts that I feel are important. So there's this E-greedy part here. You have to have some way for your agent to actually explore the environment and take care of an exploitations trade-off. By that, I mean, you need to have your agent sufficiently explore the environment as well as exploit what it has learned and what it already knows. And this is where this E-greedy policy comes in as a start. Essentially, it says you define some small epsilon and essentially you say, with probability epsilon, take a random action. With probability 1 minus epsilon, or maybe the other way, then you exploit what you already know, what you think will give you the best reward at a particular state. And then it makes this update. Quick thing about this, with Q-learning, there is this thing called a Q table that is indexed by the action and the state and essentially gives you the Q value at a particular state for a given action. It's essentially, a Q value is like some sort of metric, the quality of being at a particular state and taking an action, to put it very simply. But yeah, it uses that Q table to reference old values when you make an update, except at this part by the A, you're essentially inputting the action that will get you the highest Q value. There's another algorithm called SARSA, which goes exactly the way this goes, except over here, you input the action that you get from your E-greedy policy, the policy that you are using to explore. And you make an update here, like S prime into S, you make another update saying A prime into A for actions. So this is practically what you want. Like, this is the bottom line in general when you're doing a reinforcement learning model and training it. You want some optimal policy, right? With value-based algorithms, you essentially have a metric for all your states or state actions, and you would derive the policy from that. So for this robot, it will try and pick the reward that is highest at each state, right? This isn't like Q-learning, which does states and actions, but there is another algorithm that would just provide a metric for just the states. But as a robot, or even just as a human, if you were here, you would try to go for the highest reward. So here you would pick -5 instead of -7 and just try and go to the goal. On the right, these aren't like related or anything, but if you did have let's say a policy-based algorithm, it would just learn the policy directly, and essentially this would be how it looks. You just have at each state you refer to your policy and it says take this action, up, down, left, right. So let me just finish up with these slides. So what if you have too many states and too many actions? That's where you bring in a neural network. So with Q-learning, you give your function a state and an action, and it gives you your Q value. With deep Q-learning, for example, you give your neural network your state, and it gives you the Q value for all possible actions. And I guess you'd pick the action with the highest Q value, but yeah. And just a quick aside, with agents in the deep reinforcement learning side of things, it's best to have like an experience replay buffer that will store each of your transitions, and then you would have to sample from it and then use it to make any updates you need to your network and so forth. So that's the end of my slides. I just want to show, oh, I stopped sharing, my bad. That's the end of my slide. I just want to show some algorithms in action. So I just want to speak a bit about Gymnasium. This is a library framework that you use for creating reinforcement learning environments and your agents. It really helps like simplify that side of things. Let me just, oh gosh, I hate this. Let's go a little bit of Gymnasium. Okay, so Gymnasium is essentially, actually, let me not show this part. Let me just show in here. So in Gymnasium, they have like a set of environments that you can use to try and like maybe train them, play around with reinforcement learning a bit, you know. Let me show you this. Okay, so this environment is called cliff walking. Essentially, there's a start state, which is the chair, and then there's a goal state, which is, I think, a cookie. And there are like other terminal states, which is the cliff. So essentially, whenever it goes into the cliff, it gets a reward of -100, and then the episode ends. So it starts again. And every time it walks on each of these squares, it gets a reward of -1, and that's it. So essentially, when you pick your rewards for your environment, you have to do it in a way that incentivizes the agent to do what you want. There isn't any reward for getting to the cookie, but yeah, to get from here to here, it's just also -1, but that's enough. That's enough for learning purposes. So let me just end this. So I showed you guys Q-learning. So Q-learning is pretty greedy. It's kind of it's known to converge to an optimal policy, but SARSA, the other one, is more conservative and is known to get to a near optimal policy. So I guess I'll just show you how that looks like. That is rough. Oh, no. My bad. I forgot to comment this out. Okay, so this is Q learning in action. It takes 13 steps to get to the cookie. And essentially, the highest reward that this guy can get is -13. So as you can see, it is going just around the cliff. That is the shortest part of the cookie, and all works out fine. Now, if I show you Sarsa, this guy tries to avoid the cliff. And I guess someone would want to use Sarsa over Q learning because, I mean, let's say you're doing reinforcement learning on like a robot or something. You don't want your robot to keep getting damaged or something. You don't want disasters to keep happening as you train something. So it definitely helps in those cases to try and avoid these disastrous effects. So over here, just a quick aside, I have this class. I initialized my Q table. I used a dictionary. I could have used like a NumPy array or something, but I use the dictionary here. This is my epsilon greedy policy. I say get a random number. If it's less than epsilon, get a random action. Otherwise, get your best action. And here is how I made the function to get my best action. It essentially says, give me the action that gets me the highest Q value at a particular state. And then this is where I implemented that algorithm that I showed earlier. Over here, I got the best action before adding it to that max Q. And then for the Sarsa, instead, I just used the same policy I used to explore, which is epsilon greedy. Okay, so a little bit about, in Gymnasium, you can make your own environments to try and test. I just want to show, this was like my attempt at like making a tic-tac-toe environment. So with Gymnasium, you need to inherit the class and make a couple of functions. Like you have to make a step function, at least a step function and a reset function. I don't remember if you have to make a render, but I don't think so. So you have to make a step and a reset. A step takes in an action and tells you what your next state is going to be. Like it tells you all this information, like what's the next state, whether what reward you got, whether the simulation is done, like have you reached like a terminal, and then truncated, that is a Boolean to also tell you like if the simulation is done, but maybe in expected circumstances, but not the way that you initially set the environment to go. Like maybe instead of letting a robot get into a hole or something, you're like, it's truncated. Maybe I just removed it or something. And then this is like a dictionary if you want to add in any extra information. So with this TikTok, oh my goodness, tic-tac-toe environment. I essentially have this box and the players is 1 and 2 and then empty space is a 0. So I'll just show you how, I mean, my render function isn't anything fancy. As you saw in the other one, it was like a pie game, but I'm just printing out the board. Let me just show this. So as you can see here, it's just a quick simulation, people just playing randomly, and it tells you who won. It randomly assigned which player to your particular agent, and then it played against another random player, and then it tells you if you won or not. So now I want to talk a little bit about stable baselines. So stable baselines 3, this is a deep reinforcement learning class that helps you, well, try out deep reinforcement learning algorithms. Just play around with it, because when you do it yourself, it can be very cumbersome, lots of math involved, and a lot of things that you have to consider. But when you try and learn a bit about the hyperparameters of certain algorithms you want to use, then and how the certain algorithms work, then it can be easy to try and see how things would maybe fare out in this library. So these are like some of the algorithms that are available to try and use in stable baselines, like a deep Q network. It also works with gym environments. That's why I'm mentioning it. It can tell you what types you can have for your action space, what types you can have for your observation space. It can give you examples and how you can view your results. And it's just really easy to play around it, I believe. So I just want to show another example. So this guy is Lunar Lander. This is another gym environment called Lunar Lander. Essentially, you have this, I don't know what to call it. What would you call it? Huh? Icon? Okay. Okay, let's say maniki. Sure. This maniki spaceship. So essentially, its goal is to land within this. You want to train it to land on this part in between the flags, like smoothly. So let me just speak about the rewards. So as it says, from moving from the top of the screen to the landing pad, you get 100 to 140 points. If the lander moves away from the landing pad, it loses a reward. If the lander crashes, it receives an additional negative 100 points. If it comes to rest, it receives an additional 100 points. Each leg with ground contact is plus 10 points. Firing the main engine is negative 0.3 points each frame. Firing the side engine is negative 0.03. And by solved, you mean you're doing a good job. It means if you get to 100 points, things are great. But essentially, this reward system is here to encourage the lander to use as little fuel as possible and land safely within the goal. So I just want to show, let's say, this. So this is how using stable baselines goes deep reinforcement learning. It's 25 lines of code that I have here, where you could just import from stable baselines your particular algorithm you would see on like the documentation. And then this part is just for making the directories for logging, for making logs and adding the models, because I want to save them. And then you can make use of TensorBoard, which I'll get into. It's a way of you visualizing your practically how training is going, the rewards, the average rewards you're getting, the length of each episode, and so forth. So without further ado, so over here, I made like a models directory. I made a directory for the logs. Over here, I essentially define my model. There's all sorts of things you can now add inside. You'd have to look at the documentation so that you can add all the hyperparameters you'd want. But I'm just going to use the defaults here. And then here are my time steps. After every iteration, it will save, like, let's say the first 10,000 time steps, the model at the first 10,000 time steps, the model at the 20,000 time steps mark, and so forth. So let me run this. So I have a terminal, and I guess I'm just let me try to find a. Actually, let me write it out. Okay, that's gonna take a while. But in the meantime, when you're running these models, you might wanna start your TensorBoard up. Actually, I think mine is already up. Let me start it again. Give it a second. Okay, so currently the training has started for this environment, and it's just giving me the rollout. Over here, I have my tensor board started up, so I just need to go to this link. Let me see. Okay, so this one is a model that I had already ran before. I need to set this. I need to set the range. And let me, I wish I could like zoom out. Let's see if I could zoom out. Okay. So this is the model starting up. Let me try and, sorry, give me a second. Negative 400 minus 400, just to see. Okay. So the model has started at 11:07 a.m. and essentially this model PPO, proximal policy optimization, that's the model that one of the reinforcement learning models that I'm currently using. It's a policy-based algorithm, and it's essentially learning the algorithm directly using a neural network. So, okay, I'm not gonna try and just wait until things get better here. I just wanted to show this one, I think. Gosh, why isn't da 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 da. Okay, cool. So as you can see, the model that I had already ran I ran this in like the AMs. It took about an hour, like over half an hour, no, over an hour and a half. And essentially it did really well. It went from like the negatives into the positives over 200 average. And so I want to just show you how the environment looks when when you haven't trained it versus after I've trained it. And as you can see, the one that I just started now is also picking up really quickly. So let me go. Test. Oh, it's gonna take a bit. Yeah. Okay, it's starting up. Okay, so this guy is being random. Like oh, I'm going too long. This money is being really random. It's not too sure what it's doing. And sometimes it makes it, sometimes it doesn't. But that is life. So let me show you after I've like trained the model. It's so easy to like, let me show you my model. So here I have these zip files that I kept saving at like 10,000 step increments. I could like maybe look at the board and say, oh, I want this model at this time step, or that model at the end. Or yeah, you just look at where there's like 10,000 by the step counts and be like, okay, maybe I want to load that model, see how that did. But I'm just gonna choose like the last one and then let me run it.
Amma, sorry to disturb you.
Be done.
Yeah.
After this one. Give it a second. I don't even know if this thing started. So yeah, now you can kind of see that it's trying to be very careful, way more careful in like landing. It's taking a while to end its episode, but geez. Right now it's taking a while to end the episode because it landed on just a vertex. So now it's like, okay, that is so unfortunate for me because I have to like end this. But essentially what you would have seen, you would have seen this lunar lander try very carefully to land in the middle. Earlier, you didn't really see too much carefulness. Sometimes it would like just fly away or go off to the side. But if you kept checking this out, then it would have just kept trying to land right in the middle. Let me try it one more time. Let me play it one more time.
We're really running out of time, right?
Okay.
Sorry.
It's okay. Cool. Oh yeah, here. You see, it's trying to really land in the middle. You know, earlier it wasn't. It was just flying all over the place, and that is because of deep reinforcement learning. You could, and just a quick aside. When you want to train these things, I mean, let's say you just want to try another algorithm for the hell of it. You could just import the other algorithms. Let's say like DQN over here. You could just replace this PPO with DQN, replace this PPO with DQN, and then now you can try this this. And also you would have to take into account like the hyperparameters that you have to add, okay? Because there's a lot to this. But the point is that replacement is much easier than if you were, and your environment is in its own space that you would have made by yourself, like I showed you, and things are just easy to swap and change around without, I don't know, you racking your head too much, I guess. And yeah, it's enough to start playing around with, at least. Thank you for being here.